Hey everyone, welcome to this module on building reliable data lake with Spark and Delta Lake. So in this module, we'll first understand why Delta Lake is required. Then we'll see how Delta Lake works under the hood. This is super important to understand. And then see how Delta Lake provides asset guarantees. Next, we'll see how to create Delta tables and what goes into transaction log. We'll then look into various options to add the data to the table and then perform DML operations on top of it. Next, we'll see how Delta Lake maintains data quality using table constraints. And finally, we'll discuss a very interesting feature, the time travel. So let's get started. Let's start by understanding what's a need for Delta Lake. But first, let's see what's a data lake. A data lake is basically a concept. It's a cost-effective central repository to store all types of data, whether it is structured, semi-structured, or unstructured data. You can store the data at any scale, and it is in the form of files. For example, you can use Azure Storage, Amazon S3, or even on-prem data center to create a data lake. Now Spark works very well with data lakes. So let's see how it writes the data to data lake. Let's say you have a Spark cluster and a data lake. Now you want to run a job to process sales data and write the output in CSV format to the sales folder in data lake. To do that, Spark will create multiple tasks to process the data in parallel. And these tasks will parallelly write the files in data lake folder. These are also known as partition files. So the final output is stored in these multiple files. Now before we move ahead, let's see what are asset guarantees. In databases, each transaction you perform provides you with these guarantees. A stands for atomicity. This means that in a transaction, either all the changes will be written or no changes will be written. For example, if there is a table and you are writing two records to that table in a transaction, either both the records will be stored or none of them will be stored. Partial output will not be written. So the transactions have atomic behavior. Then second is consistency. This means that data will always remain in a valid state before and after the transaction. For example, say you are storing bank balances and you define a constraint that balance cannot go below 0. So if balance is 100 and you are trying to withdraw 200, the transaction will not succeed. This ensures that data remain consistent. Make sense? The third one is isolation. This means even if multiple transactions are running, they should not interfere with each other or affect data consistency. Let's say a table has 3 records and a transaction is writing 2 more records. One is written and the other one is about to get written. Now if a reader is reading from the same table, the read transaction will only see 3 records and not the new data till the write transaction is complete. This ensures that each transaction runs in isolation. And finally, there is durability. So once the data is committed and changes are stored, they should persist even if any system failure occurs. So these asset guarantees on transactions makes database a reliable storage platform. But here is the thing. Even though data lake is cost effective, provides scalability, and store all types of data, but it does not provide asset guarantees. So let's see what problems can occur. It's very important to understand this. Let's say you have a folder in data lake to store sales data. And 2 partition files are already stored there, part file 1 and part file 2. Let's see what happens if there is a job failure while appending the data. Say there is a writer process that wants to append 2 more partition files using 2 tasks. So it starts to write 2 files and 1 file is written. Now let's say the job fails while processing the part file 4 with a runtime error like division by 0. Now carefully notice that folder contains partial data. On the other hand, say a reader wants to read the data in sales folder. So it will read part files 1, 2 and 3, and this means it's reading partial or inconsistent data. So a failed job breaks the atomicity guarantee and puts the data in inconsistent state. Make sense? Let's take another example and see what happens if there is a failure while overwriting the data. Once again, there are 2 part files present in the folder. Now a writer process wants to overwrite the existing data. In Spark, overwrite is a 2-step process. Delete the existing files and then write the new files. So first, writer deletes the existing files and then starts to write the 2 new files. Once again, say 1 file is written and the second file is still getting processed. At this point, the job fails with a runtime error, so the second file could not be written. Now a reader process wants to read the folder, so it will only read the new part file 1. This means it's reading inconsistent data and we have lost the previous data as well. So this failed job has broken atomicity and consistency, and durability is not provided because existing data is lost. Alright, now let's see what happens during simultaneous read and write. Let's say a writer process wants to append 2 more partition files, part file 3 and part file 4. File 3 is written while file 4 is still getting processed. Now at this point, let's say a reader process wants to read the data. So it reads the whole folder while writing is still in progress. Now carefully notice it is only going to read 3 files present in the folder. And once again, this means reader is reading inconsistent data. This is where isolation is so important. Any data written by the writer should not be visible to the reader till it is committed. But since there is no mechanism in Data Lake to check this breaks the data consistency and isolation of transaction. And finally, let's see what happens if you add data with a new schema. Let's say the current dataset has 3 columns. Now the writer process wants to append 2 new files. But this time, the output will have 4 columns. So it will write 2 files to the folder. The new output files have 4 columns, but no schema validation is performed before writing the data. And this is where the problem starts. When the reader process starts reading the folder, it does not know how many columns are there. If it reads file 1 or 2 first, it will consider 3 columns. But if it reads file 3 or 4, it will think that there are 4 columns. And this does not provide a consistent view of the data because there is no schema validation before writing. Make sense? So as you have seen, there are several challenges associated with Data Lake. It can have data reliability issues. If there is a job failure while writing, it may lead to data corruption, and you cannot even roll back the changes. No data validation is performed while writing, so a column could be written as an integer in one transaction and a string in another. And there can be consistency issues while reading the data. Also, if you have streaming data in your projects, it can be tough to handle along with batch data. Now, one of the biggest drawbacks is that you cannot perform updates and deletes on files easily. And because of this, implementing GDPR CCPA or other compliances becomes a challenge. Then there can be data quality issues. As you saw, schema is not verified before writing the data. And unlike databases, you cannot apply checks on data. You have to handle all these things in your code. There can be query performance issues on data lake, which we'll be discussing later. And it's also difficult to maintain historical versions of data. So because of this, storing data in data lake becomes challenging. This is where Delta Lake comes in and can help us solve these challenges. But the question is Delta Lake the only option? No, there are other projects in the same space, like Apache Iceberg and Apache Hudi, that work similarly to Delta Lake. Sounds good? Now that you have seen why Delta Lake is required, let's see how it works. Delta Lake is an open source storage layer that brings reliability to data lakes. Think of this like a small utility that you need to install on your Spark cluster. Alright, so first let's see how to save the data in Parquet format. If you are not aware about Parquet, basically it's a columnar format for files. Let's say you have created a data frame in Spark. Now when you save this data frame in Parquet format, it will create and store multiple partition files in Parquet format. On the other hand, in case of Delta format, first you need to deploy Delta Lake component on Spark cluster. Once again, you have a data frame. Now when you save the data frame in Delta format, it will again write the partition files, and these files will be in Parquet format. Till this point, it's exactly the same as previous case. But along with Parquet files, it also stores a transaction log. And this is where the magic starts. The transaction log contains the log of every single operation that has been performed on this data. Alright? But before we see what's in transaction log, let's see how you can write the data in Delta format. On the data frame, use the write property, define the format. For Delta Lake, use Delta format. Just like you can also use other formats like CSV, Parquet, etc. And then use the save method. This will store data in Parquet format along with transaction log. Simple, right? Let's dive in a bit deeper. Let's say you want to store customer data in Delta format. Now inside the customer folder, Spark will create a subfolder called _delta_log. This is where the transaction log will be stored. Now on first write operation, let's say it creates two part files, 0.parquet and 1.parquet. But since you are storing the data in Delta format, Spark will also create a file in _delta_log folder called 0.json. This is the first transaction entry. Now you want to insert more data. This writes a new part file in customer folder and then adds one file in log folder, 1.json. This is the second transaction entry. In the same way, during third write operation, one Parquet file is added and a log entry is created as well. This means for each write operation, the part files are written first and then a transaction log file is added to _delta_log folder in JSON format. And remember, only when the log file is written, the transaction is considered complete, otherwise not. Make sense? Now let's see how read operation works. For each read operation, first transaction log files are read, and after that, partition files are read based on the information in log files. This means it will first read all the log files 0, 1 and 2 and then read all 4 part files based on the log information. Alright, now that you have seen how read and write operations work, let's dive further into transaction log. Let's say you're writing the customer records for the first time. Spark has created two partitions files for this. The dataset has two columns, ID and name, and each file has two records. Then, as you know, 0.json file is added to the log folder, and then the transaction is complete. Now notice the log file contains information that part file 1 was added and part file 2 was added. Sounds good? Now let's say you perform an insert operation, and this is going to append one more file with new data. First, part file 3 is added with two new records, and then 1.json file is added to the log. Once again, it mentions an add operation, and part file 3 is now part of data. And now let's see how an update operation is performed. Let's change the name from A to AA, where ID is equal to 1. Currently, record for ID 1 is present in part 1. Now performing an update is very tricky. So what will happen here? Delta will create a part 4 file. It will copy all the unchanged rows from part 1 to part 4. This means record for ID 2 is copied as it is. And then it will add the modified row for ID 1. Sounds good? It will then write 2.json in transaction log. Now notice, first it mentions that with current transaction, part 1 is no longer required. This is because all unchanged data from part 1 has been added to part 4, and modified rows have also been added to part 4. So remove part 1 and then add part 4. This is how update operation is performed. Now let's see how to read the data. First, it will read log files with 0.json being read first. So according to it, it collects the information to read part 1 and 2. Then according to 1.json, it needs to read part 3. But according to 2.json, part 1 is not required. So it will remove part 1 from reading list and then add part 4 to reading list. So this means to read latest data, you need to read part 2, 3 and 4. Now based on this, the final output is prepared. It contains records from part 2, from part 3 and part 4, which includes a modified row. So that's how transaction log of Delta Lake is used to read and write the data. Interesting, right? At a high level, let's see what features does Delta Lake provide. It provides asset guarantees. So even if there are job failures, data is not corrupted. And it provides data consistency while reading the data. Then you can perform inserts, updates and deletes on the data with significantly less overhead. It also enforces the schema that helps in preventing bad data being added. You can also look at previous versions of data using time travel. Next, it can seamlessly handle batch and streaming data. You can also apply various data quality checks, and it can significantly improve query performance using statistics. And there is much more. Keep a note of these points. We'll discuss them one by one. So to summarize, Delta Lake provides database-like features on top of Data Lake. Now let's see how Delta Lake provides asset guarantees. Previously, we discussed what are asset guarantees on transactions. Let's quickly summarize that. A stands for atomicity. This means either all changes or no changes should be written for a transaction. C stands for consistency. So before and after a transaction, data should remain in a valid state. Then there is isolation. Each transaction should run in isolation, and it should not be affected because of other transactions. And finally, there is durability. This means once a transaction is committed, the data should persist even if there is a system failure. So let's see how Delta Lake provides these guarantees. Let's say you are storing the data in Delta format. Two part files have been stored, and a log file is stored corresponding to that. Now let's see what happens if there is a job failure while appending the data. Let's say a writer wants to write two part files. One file is written while other is still getting processed. Now at this point, the job fails with a runtime error. This means part 4 could not be written. But also notice that no entry is made to transaction log. That's what makes a transaction atomic. Now when a reader wants to read the data, first it reads the log file. And since 0.json only points to part files 1 and 2, it only reads these two files. Carefully notice that even though folder contains partial data in terms of part file 3, it will ignore that file. And that's why reader is able to read consistent data. So even in case of job failure, the dataset will not be impacted. Sounds good? Now let's see what happens if there is a job failure while overwriting the data. Let's say a writer process wants to overwrite the existing files by providing two new files. As you saw previously, Spark deletes the existing files. But in case of Delta format, existing files are not deleted. Now it will start writing two files. Once again, one file is written and there is a runtime failure. Now even though partial data is written, no entry is made to transaction log. And I'm sure you can guess this one. If a reader wants to read data, it only reads part files 1 and 2 based on the log, right? So the reader is not just able to read consistent data, even the previous data is not lost. This is how Delta Lake provides a durability. And finally, let's see how simultaneous read and write work. Once again, writer wants to write two more files, so it starts writing the files. File 3 is written to the folder, while file 4 is still getting processed. But at the same time, a reader process wants to read the data. So it reads the log file 0.json, and based on the log, it only reads part files 1 and 2. This means reader is not reading any partial or dirty data while writing is in progress. That's how the writer process is running in isolation. Also notice, once file 4 is ready, it will be added to the folder and then an entry will be made in the transaction log. So next time, when a process wants to read the data, it will read two log files and then read 4 part files. So as you have seen, this is how Delta Lake provides asset guarantees. Now let's see how to create a Delta table and store the data in Delta format. Let's create a new notebook. You have already seen how to install Delta Lake for Jupyter in the setup module. Now let's create a Spark session. To use Delta Lake, add the configuration. First, add a package for Delta Lake. Carefully notice the version number. If you have installed a different version, make sure to change this setting. Then add this setting to use Delta Lake with Spark session, and second one to create Delta tables. Let's run this. Now let's create the schema for yellow taxis and read yellow taxis file. You have seen this in previous modules as well. Let's execute this. And there are 19 columns in the file. Now let's use the command to create a database. This will create taxis DB if it doesn't exist. Let's run this. Now let's save the output of YellowTaxi.df as a table and store the underlying files in Parquet format. So on YellowTaxi.df, use the write method. Let's specify mode as overwrite. This will overwrite any existing files. Let's partition it by vendor ID. Provide the format as Parquet and specify the path, which is yellowtaxis.parquet, and the table name as taxisdb.yellowtaxisparquet. Let's run this. Now before we look at the Parquet data, let's save this as a table in Delta format as well. The command remains exactly the same, but this time let's use the format as Delta, and the output folder name will be yellowtaxis.delta and table name as taxisdb.yellowtaxis. Let's execute this, and the data is now saved. Now let's open the path where data has been saved, and in the output folder you can see two folders, one for Parquet and one for Delta. Let's look at Parquet output first. Notice there are separate folders for each vendor ID because of partitioning. Let's check data for vendor ID 2, and you can see multiple partition files have been created of around 14 MB each. In the same way, you can check for other partitions as well. Now let's check the Delta output. Once again, you can see different folders for vendor IDs. Let's open folder for vendor ID 2 and notice there are partition files. This is exactly the same output as you saw in Parquet, right? But at the root folder, I'm sure you have noticed the presence of folder _delta_log. Let's open this. Since there is only one transaction, notice the presence of one JSON file, 0.json. Let's open this file. You can see commit info, there is metadata, and there are add file operations. Since there is a lot of information here, let me show you a sample log entry. I have only kept limited information here. Now, as you saw, there is commit information. This contains time at which commit was made and who made the commit. Then what operation was performed. Since we wrote the data, the operation type is write. And then there are operation parameters like mode as override. It also contains operation metrics like how many files, bytes, and output rows are written. Then it also stores metadata. This includes the schema like column name, its data type, if it's nullable, and other properties. Sounds good? And finally, it contains file operations, like which files are added, removed, etc. And the path of the files is stored. So you can see a lot of information is stored in each transaction log. Back to the notebook. Let's run a command describe history to check the audit log. This shows the transaction log of Delta tables and only work for Delta tables. Let's run this. And you can see currently there is only one transaction done on the table, which is create or replace table as select. It shows some of the information from the transaction log, like version number and timestamp, very important, user and the operation information, and operation metrics, number of files, output rows, and output bytes. That's why this is a very useful command. Now let's rerun the command to save as Delta table. Remember, this is using overwrite operation. Let's run this. Now will it actually replace the existing files? The answer is no. Let's see why. Let's open the yellowtaxis.delta folder and go to folder for vendor ID 2. Notice the files from first transaction and the files from second transaction. If you remember from previous clip, in case of an overwrite operation on Delta table, the existing part files are not deleted. It first adds new part files and then add an entry into transaction log. So if an overwrite operation is running and someone tries to read the data, the read will still succeed. This helps to provide consistency in read operations. Make sense? Let's run describe history command again and see that there are two transactions. The first transaction wrote 9 files and the second one also wrote 9 files. But the latest transaction only refers to the newer 9 files. Now let's see another option to create a table, which is to use a typical DDL command. Let's drop the table first and then remove the folder for delta from storage. Now let's use create table command to define the table. Provide the column names and their data types. You can also provide comment for each column and set a column as not null. By default, each column will be nullable. Then specify type as delta. The default type is Parquet. Provide the location to store the files and a column for partitioning. Just like columns, you can also add a comment for the table. Let's execute this. And this creates an empty table. Remember, creating or altering table is also a transaction. As an exercise, run describe history command to check that. Now let's run a command describe table extended to check table details. You can see all column details. Notice the comment against a column. It is partitioned by vendor ID. There is the comment for the table and the provider is delta. So you can see delta table can be created and described in multiple ways. Now that we have created the delta table, let's see how to add data to it. Let's see different options to insert data to a table. You can do that by using insert command in SQL. You can also create a data frame in PySpark or Scala and then append it to delta table. Let's see these options one by one. Back to the notebook. We already have an empty table, yellow taxis. Let's add data to it. First, let's use the insert command. This is a typical SQL command. Use insert into and provide the table name. At the time of recording, there is a bug in providing column names, so let's keep it commented. And then provide the values. Notice this record belongs to vendor ID 3. Let's run this. And this inserts one record. Let's use a select query to verify this and execute this. There you can see one record in the table. During development, it's very important to check the transaction log at each step. So let's use describe history command again. Notice it has created a new version and performed the write operation. Now notice the operation metrics. It has added one partition file and one row has been inserted. Now let's see the second option, appending a data frame to delta table. So first, let's read a file called yellowtaxis_append and show the results. Let's execute this. So this file basically contains 3 records where vendor ID is 3. Now let's use this yellowtaxis_append_df. Let's append this data frame to delta location. On the data frame, use write operation. Now define the mode as append and then define partition by clause. Specify format as delta and provide the delta folder path. Let's execute this. And this should append data to the delta folder. To verify, let's check the data in the table. Let's run this select command. And there you can see 3 new records in the table. Now let's check the transaction log. Let's run this. Notice that using insert command or appending a data frame, both are write operations, with mode as append. And see the operation metrics. One new file has been added with 3 records. And now we have 2 partition files holding 4 records. So in the same way, let's append data from yellow taxi DF to delta table. Let's run this. And data has now been appended. Let's check the count now. And you can see the table now has 3.6 million records. So these are the different options to add data to a delta table. One of the great features of Delta Lake is that it allows to perform all DML operations on data. So let's see how to run update, delete and merge on delta tables. Back to the notebook. Let's see all records for vendor ID 3. Here, the input file name function will return the file in which the record exists. Let's run this. Notice there are 2 files that contains vendor ID 3 data. One file contains only 1 record and second file has 3 records. Now let's update the record with pickup location ID 249. This is present in the file which has 3 records. Currently, the passenger count is 1. Let's update this value. Ideally, your table should have a unique key if you want to do specific updates. Now let's run the update statement. Let's set the passenger count to 2. Let's execute this. And you can see 1 record is affected. Let's verify if the record has been updated successfully. And you can see passenger count has been set to 2. Now let's check the folder. Let's open vendor ID equal to 3 folder. Previously, there were 2 files, but after the update, 1 more part file has been added. Now let's open Delta Log folder and open the JSON file for latest transaction. There you can see 1 file has been removed, which had the original record, and a new file has been added. This new file will now have unchanged rows and the updated row, right? You can also check the commit info here, or you can check it using describe command. So let's run the describe command. Notice the operation is of type update. Now in the operation metrics, see that number of files removed is 1. Number of added files is 1. 2 unchanged rows were copied. And 1 row was updated. Now delete operation is very similar. Let's see that. First, let's check if table contains a record with vendor ID 3 and pickup location ID 151. Let's run the query. And the record exists. Now let's run the delete statement. Use delete from table and specify the where clause. Let's execute this. And this affects 1 row. You can verify this by running the same select query again. And the query did not return any result. Let's check the transaction log. And there you can see there is a delete operation entry. It even shows the predicate that was used in the query. Now notice the metrics. 1 file was removed. A new file has been added. This means unchanged rows were copied from the old file to the new one. 2 unchanged rows were copied and 1 row was deleted. As an exercise, go to the folder and try verifying this. So this is how delete works. Finally, let's see how merge command works. A merge command can perform multiple inserts, updates and deletes all in a single transaction. First, let's read a set of records from a file which is yellowtaxi_changes and create a new data frame yellowtaxi_changes_df. Let's run this. And you can see there are 4 records in this file. The first 3 records are already present in the table and the last one is not. Now on Yellow Taxi Changes DF, let's create a view and let's name it as Yellow Taxi Changes. And this creates a view. Let's run a query on this view and there you have 4 records. So we are now querying the data frame. Now let's define a merge statement. With merge into command, specify the table name that you want to update, which is taxisdb.yellowtaxis, and give it an alias target. Then in the using clause, specify the source dataset. In this case, it is the view Yellow Taxi Changes. And let's give it an alias source. And then define the join conditions between source and target datasets. Even though this is not a unique combination, but for demo purpose, let's join on vendor ID and pickup location ID. Next, define the action when condition matches between source and target. When matched, let's update the record in target table by taking values from the source dataset. For now, let's only update payment type. But of course, you can update multiple columns separated by commas. If you want to update all the columns, just use update set star. Now in the same statement, define the action when record exists in the source but does not exist in the target. This is defined by using the clause when not matched. Notice you can even add additional checks like pickup time should be greater than or equal to 1st of March 2022 and then provide the insert statement as an action. You can even use insert star. Sounds good? Let's execute this. So a total of 4 records were affected in the Yellow Taxis table, 3 records were updated, and 1 record was inserted. Now that you know how to check transaction log, use describe history command and check out operation, its parameters and its metrics. So that's how you can run updates and deletes on Delta table and even merge data between 2 datasets. Another way of maintaining data quality is by applying table constraints. Let's see how you can apply them on a Delta table. There are 2 types of constraints that are supported. First, there are not null constraints. This prevents a column from having null values. And second, there are check constraints. Here, you can define conditions on the table, and these conditions are enforced on the data inserted in the table. Let's see how they work. Back to the notebook. Let's first see the not null constraint. While table creation, we had set not null constraint on pickup location ID. Now at the time of recording, there is an open bug that does not allow setting a column as not null after table creation. But this should get fixed soon. And this is the syntax to set it as not null. Here, let's alter the table Yellow Taxis and then change the column pickup location ID and drop not null constraint. Let's run this. And this drops the constraint. Let's check the transaction log. And you can see this is a change column operation which has also been logged. Alright, now let's see the check constraint. A check constraint helps to enforce certain conditions on the Delta table. So let's alter the Yellow Taxis table and add a constraint called passenger count check. Use the check keyword and then define the expression. Here, let's say the passenger count should be less than equal to 5. Let's execute this. And notice it throws an exception. Since table already has records with more than 5 passenger count, this constraint cannot be applied. As an example, let's change the expression. You can even add multiple conditions here. like count should be less than equal to 9 or it should be null. Let's execute this. And this successfully creates a constraint. Let's verify this by trying to insert a record where passenger count is 20 and execute this. And you can see it threw an exception because of constraint violation. Now, if you want to drop a constraint, you can use drop constraint clause and provide the name. Let's run this. And this has now removed the constraint from the table. And finally, let's check the log using describe history command. And notice the two operations, add constraint and drop constraint. In fact, it even shows the expression. So that's how you can use constraints to maintain data quality of your Delta tables. One of the most interesting features of Delta Lake is time travel. Let's see how to access the data using time travel. Let's take an example. Say you want to store customer data in Delta format. With first transaction, 2 files have been written and a log file as well. Let's say this transaction happened at 10 AM. Then second transaction happened after 10 minutes at 10:10 and 1 file was appended. Finally, the last transaction happened at 10:20 AM and another file was added. Now let's run a query, select star from customers. This will go ahead and read the current version. This means it will read all the transaction log entries and correspondingly, it will read all the part files. Right? Now let's change the query. With the table name, let's add the version number we want to read. So let's use select star from customers version as of 1. This means let's read the snapshot of data which was committed with version 1. So it will only read the log entries till version 1. And because of this, it will read part files 0, 1 and 2. This is what is known as time travel. So you can even read a previous version of the data even if it has been updated or deleted. Interesting, right? And not just by the version, you can also read the data snapshot using timestamp. Let's change the query. Select star from customers, timestamp as of 10:05 AM. This means let's get the data snapshot at 10:05. Now at 10:05, the latest version was version 0. So it will only read log entry 0 and extract part files 0 and 1 corresponding to that. So time travel allows to access and even restore the previous snapshot of data, even if it has been modified or deleted. And you can access it either using version number or timestamp. This can be extremely helpful if data has been accidentally modified or when you want to compare the latest data with previous versions. So let's see how this works. Back to the notebook. Let's first check the passenger count for a combination of vendor ID and pickup location ID. And you can see the passenger count is 0. So let's fix it. Now let's run an update command and set the passenger count to 1. So let's execute this. And now the passenger count has been updated from 0 to 1. Let's check the table history. And you can see an update operation has been performed. Notice the latest version number. Now let's check if this record was present at version 0. So let's run the same select query. But along with table name, let's specify the version number 0 and run this. No result. So this record was not added during initial load. Make sense? So let's modify the query and check the value of passenger count at a prior version. Let's execute this. And it's showing passenger count as 0. Remember, the value in latest version is 1. So that's how you can check table history and perform time travel using version number. And as we discussed, it can also be done using timestamp. So in the query, use the clause timestamp as of and provide the timestamp. Let's run this. And you can see count as 0. Remember that timestamp need not be exact when the transaction happened. At any given timestamp, whatever is the last commit, that will be considered. Now that you have seen how to query the previous version, let's see how to restore that version. It's very simple. Use the restore table command, provide the table name, and provide the version number which you want to restore. Let's run this. It will take a bit of time, but you can see the number of files after restore, the number of removed, and the number of restored files. And that's it. Let's check the log again. Notice the operation as restore and even the version number which has been restored. Now let's run the same select query, and this shows passenger count as 0. So the updated value of 1 has been overwritten. So time travel feature is extremely useful to protect and restore previous versions of data. In this module, we saw that Delta Lake is an open source storage layer that brings reliability to data lakes. And it can help to build data warehouse-like features on top of Data Lake. Now when we store the data in Delta Lake, the data is actually stored as Parquet files. But along with that, it also stores the transaction log. And this helps to provide asset guarantees on Delta Lake. Then, if we write the data in this format, the partition files are written first, and then an entry is made into transaction log. And in case of reads, the log is read first and then the partition files. Next, we saw how to create a Delta table. The Spark table in Delta format is called Delta table. We also saw that each log entry contains commit information, schema, file operations, etc. Then we worked with various options to add the data to the table. We can append the data frame using Python or Scala, or we can use insert command in SQL. We also saw how to run DML commands like update, delete, and merge, and how it is handled in Delta Lake. Then we can also maintain data quality by applying not null and check constraints on the table. And finally, any data that has been modified or deleted can be accessed using time travel. This can be done using version number or timestamp. In fact, we can even restore the table to a previous state. So that's how we can build a reliable data lake using Delta Lake. In the next module, let's see how to handle streaming data with Spark.